I think just say a few words. Welcome everyone to our today's session. We have Professor Dane Morgan from University of Wisconsin-Madison, and we have Susmita, who is our founding president of the chapter and also currently an executive on executive advisory board, I guess, for the chapter as a immediate past president. I'll hand it over to Susmita to welcome our speaker, Professor Morgan, formally. So thank you, Susmita. Thank you, Dan.
Yeah, thank you, Professor Mukherjee, for the kind introduction. Hello, everyone, and welcome back to our webinar series. I'm Sushmita Sarkar, a fourth-year PhD candidate at ETSL, and also the executive advisor of this Purdue ECS student chapter. I would first like to introduce our chapter advisory board, which is led by Professor Prof Mukherjee from the School of Mechanical Engineering at Purdue, who is our lead faculty advisor. Dr. Judy Jivarajan from Underwriter Laboratories, Corporate Fellow and Vice President of Research, is our distinguished industry advisor. We also have Professor Rebecca Chies and from the School of Mechanical Engineering, and Professor Julia Laskin from the Department of Chemistry at Purdue as our co-faculty advisor. Let me present a quick overview of our chapter activities over the past year. In spring 2021, we conducted our signature webinar series on the theme of Women in Electrochemical Science and Engineering, or WISE, comprising of a stellar lineup of women researchers from industry, national lab, and academia, both in US and abroad. This series was exceptionally well received and appreciated in the scientific community. Inspired by its success, in fall 2021, we launched a webinar series on one of the hot topics in energy storage research, solid-state batteries and electrochemistry, inviting some of the leading academic and industry experts in this area. We are proud to announce that for our effort in actively promoting scientific engagement and outreach on a global scale, we received the 2021 Chapter of Excellence by the Electrochemical Society. The theme of this year's webinar series is Modeling, Characterization, and Analytics in Electrochemical Energy Storage Energy System, abbreviated as MoChA. Today's speaker is Professor Dane Morgan from the University of Wisconsin-Madison. Dr. Morgan obtained his PhD in physics from UC Berkeley, was a postdoctoral researcher and research scientist in MIT, and is now a professor of material science and engineering at the University of Wisconsin-Madison. His work combines the thermostatistics, thermokinetics, and informatics analysis with atomic scale calculation to understand and predict material properties. A major focus of his work is energy applications, including fuel cells, batteries, and nuclear materials. But he also works in the area of thermoionic emission and defect properties in semiconductors. Dr. Morgan has had extensive interaction with industry, including consulting, serving as a vice president of research at energy startup Alien Technologies, and working with material informatics companies he trained as a visiting scientist. He is presently training or has graduated over 60 graduate students and postdoctoral researcher, and worked with approximately 250 undergraduate in research. He is the Harvey Day Spangler Professor of Engineering and the University of Wisconsin-Madison Scholar. He received multiple teaching and research awards and has published over 300 papers in material science. Today, he will be speaking on computational design of materials for solid oxide fuel cell. Dr. Morgan, we look forward to your talk.
All right, thank you very much, Susmita, and congratulations on the award for your chapter. And it seems like you all have been doing some really great things. It's very exciting. And thank you also, Partha, for the invitation. It's great to be here. Thanks everyone who's attending also. I know it's often a little difficult to attend things virtually and stay involved. So feel free if there's a question or something to jump in and ask to try and keep things engaged. But hopefully it'll be interesting. So yeah, I'm going to talk today about computational design of materials for solid oxide fuel cells. Let me just start with
Professor Morgan, can you start sharing your screen again, please?
Yeah, something just happened. Hold on. Let me try that again. That working?
Yes, thank you.
All right, great. Let me just acknowledge a number of collaborators from my group and from faculty and staff at laboratories who have contributed to aspects of this work over the years, and also a number of funding agencies who have helped support it with financial support and also computational support. Okay, so I'm going to talk a little bit about solid oxide fuel cells, just give some introduction to those of you who are not familiar with them. And then I'll talk about kind of the computational trick that we've been using, which is a descriptor approach, and I'll explain what that means. And our particular approach is based on the p-band, and I can tell you a little bit about how that works. And then talk about how we've used that to predict some new cathode materials and what kind of success we've had doing it. So let me just start with an overall introduction. So the kinds of materials we're trying to design and understand better, what we call oxygen active materials. These are just materials that can move oxygen around quickly and exchange it quickly with the environment. And as you can imagine, there are many uses for such a material because oxygen is everywhere and it's critical to so many different technologies. So they can be used in fuel cells. They can be used when you want to remove oxygen in splitting water. They can be used for sensing oxygen. They can be used for separating gases and pulling oxygen out of it. They can be used for combusting CO2 and pulling oxygen out. They have many potential applications. So it's a broad class of really interesting materials. And we're particularly interested in the application around solid oxide fuel cells, but we always have an eye to discovering materials that are just active with respect to oxygen that might have multiple uses. So let me just introduce how a solid oxide fuel cell works, in case you are not familiar with that, because that kind of motivates the work we're doing. So the basic idea of fuel cell is essentially an engine that burns a fuel, but it does it electrochemically. So in this case, we have a fuel here on the right, some kind of hydrocarbon, CH4, could just be pure hydrogen. And it's going to come in here on the right-hand side, and on the left side, we're going to bring in oxygen, and we're basically going to stick them together, and we're going to combust, right? When we mix the hydrocarbon and oxygen, they can react, and you can form water, and you can form carbon dioxide or carbon monoxide, and that is going to be a energy lowering reaction, and you can extract that energy to do work. In traditional combustion, you would create heat, and you'd use that heat energy to do work. In electrochemical cells, like a fuel cell, the oxygen gets split and is moved as an ion across the electrolyte, and then that joins with the hydrocarbon to make your water and carbon dioxide. And then the electrons in this sort of magical process of electrochemical fuel cells get pulled around an external circuit to complete the whole chemical reaction. So the secret is basically to combust your hydrocarbon with oxygen, but to split up the path of the ions, the oxygen, and the electrons, so that the electrons can go through an external circuit and you can get work out of them. So this can be an extremely efficient reaction, has a number of advantages as a way to burn fuel. Very clean, very low emission, it's often very quiet. It can run for years stably, you can adapt to many kinds of fuels, and it can be very, very efficient, significantly more efficient than traditional combustion when you do it at high temperatures. And there's a lot of different interests in using solid oxide fuel cells. One of the most widely pursued right now is distributed power supplies. Here's a sort of image of how that can work. So I think it's from Bloom Energy, where you have on the left, where you have a fuel cell out behind your building, and that provides either backup power for your building, or even you can just pump natural gas to it and it can power your building, and you can remove yourself from the grid entirely if you wanted to. So there's lots of opportunities there. One of the drawbacks of this technology, though, is it typically operates at very high temperatures, about 800 degrees Celsius, 750 degrees Celsius. Obviously, that limits some of the uses, right? It's probably not a good technology for your cell phone if it's going to be at that temperature. It also reduces the lifetime. You get interdiffusion of components. You get thermal cycling challenges. And overall, that just drives up costs. So your cost per kilowatt hour of energy goes up. And that is something you want to minimize when you're sort of developing this technology. So there's a general interest in exploring what we can do to lower temperatures of the applications. And let me just show, this is an old plot, but it illustrates kind of how how the problem arises of going to lower temperatures. This is just a plot of what's called the area-specific resistance on the y-axis and temperature on the x-axis. And area-specific resistance is essentially just, if you think of a fuel cell as flowing a current, it's just the resistance of the device. So it's directly proportional to your losses. So it's how inefficient your device is. So you want this number as low as possible. And what happens is, as you cool down your system, the total resistance goes up quite dramatically. Essentially, there's an exponential increase. And that's due to all kinds of processes that get more and more difficult to run at lower temperature. The one we're focused on is the cathode, which I should have said, well, I'll say more in a minute. The cathode essentially pulls in the oxygen and splits it. And that chemical reaction is actually fairly difficult to catalyze. And consequently, when you go to lower temperatures, it often becomes a dominant source of resistance for your system. So there's always a lot of interest in trying to develop materials that have a good ability to pull oxygen into them and split the oxygen without having a significant overpotential, which is what gives rise to this increase in the area-specific resistance at lower temperatures. So how does it work, this cathode? So here's schematically the way to think about it. So it's going to be a component of our fuel cell. It's going to bring in oxygen gas on its surface, and it's essentially going to spit out oxygen ions into an electrolyte that will then go across the electrolyte and react with your hydrocarbon fuel to complete your chemical reaction. So its key materials processes take oxygen gas and spit out oxygen 2- in solid form, like inside an oxide, so that you can move them through a solid oxide electrolyte. So here's a kind of schematic of some of those processes. Oxygen comes in as a gas, an O2 molecule. It's got to somehow split up into two oxygen. And generally, that is believed to take place by interacting with some vacancies on the surface. So you're going to hit the surface, you're going to maybe diffuse around, you're going to react with vacancies, and then you're going to move in those vacancies. Once you fill a vacancy, you're going to move by diffusion through the cathode and then down into the electrolyte as an oxygen ion. So this is essentially the process we are trying to understand. And we're trying to build materials that can do it quickly and efficiently. And one of the most widely used materials for this, and the ones we're going to focus on, are perovskites. You've probably run into perovskites if you do material science. They are kind of everywhere. This is their structure. They have two cations, an A cation on the sort of corners of a cube, a B cation in the center, and then surrounding the B cation is this kind of octahedral environment of oxygen. And a lot of them are very good at reacting with oxygen and CO2 and H2O. They have good ability to exchange oxygen in their surface, and they have good ability to transport oxygen through their bulk. So they are active oxygen materials. There's a lot of standard materials that are used. In fact, lanthanum strontium manganate and lanthanum strontium cobalt iron oxide are the two perovskite materials that make up almost all of the solid oxide fuel cell cathodes that are in use today. There is a significant solid oxide fuel cell industry. Thousands or tens of thousands are sold every year. And they basically all use these two materials, almost all of them, for their cathodes. But there's a pretty large number of other interesting materials that people have discovered over the years. They have different strengths and weaknesses, so they haven't dislodged these two as the sort of commercial workhorse. But if you study these systems, you know that barium strontium cobalt iron oxide has emerged as an exciting material, and there's a few other that I list here. And so we know that there's a pretty big promising space here. And actually, somebody once did a study of perovskites and found that you can dope into this structure, meaning you can put atoms into the A site or the B site that make up 90% of the periodic table. You can put some anions on the oxygen site as well. It's just an incredibly flexible structure. So there's really a huge space of possible perovskites one might consider. And so one of the challenges we saw is, could we use computational tools to help us work through that very large space of possible materials to target the most promising ones for further experimental study? So we're going to try and take an approach using ab initio or so-called quantum mechanical methods to try to screen or look through in one way or another the space of perovskites for materials that will be promising for exchanging oxygen and transporting oxygen through their bulk, and therefore for use as solid oxide fuel cell cathodes. So that's kind of the vision, what we're trying to do. In ab initio methods, if you're not familiar with them, basically you take as input some kind of structural information like your perovskite structure that I have here. You solve the Schrodinger equation, which is the quantum mechanical equation that describes your electrons of your system. And you get out energetics of your system, and you get out electronic structure, which is basically the properties of the electrons in the system. Things like the density of states or the band gap are the kind of things you can calculate. And just with that kind of information, you can learn an enormous amount about a material and often screen then through large numbers of materials, because these calculations are relatively inexpensive in the great scheme of things. I mean, it might take you a day to study a material and get its electronic structure. So if you have 10 computers, you can look at 10 materials a day, which isn't instantaneous, but it is much faster than synthesizing them and studying them experimentally. And here's sort of a representative example from a while back from the Sater group, who's done a lot of work in this space in batteries, in fact, where they screened a lot of potential cathode materials, looking at their ability to hold lithium, which was their capacity, and looking at their electrochemical potential for lithium, which gave you the voltage. And those are essentially just a handful of energy calculations that you can do with quantum mechanical methods. And they were able to screen hundreds, even thousands of materials and look at typical potential capacities and potential voltages. So our question was, can we take these kind of high throughput ab initio methods, so where you could automate the process, so you don't want to have to spend weeks and weeks on one material, but you do a set of relatively simple calculations that you can automate in a high throughput way. And can you use that in a way to search for better materials that can do this kind of process as quickly as possible? So here's our approach to doing that. So we took, I should probably say, if you go back to this picture, you might say, well, why don't you model, the reaction of oxygen gas on the surface of your material and study how it splits and enters vacancies. And we actually did do work like that. We spent about 5 years studying one material, trying to understand the surfaces, surface segregation, surface defect structures, which of the many possible surfaces were active. And it just turns out to be a really complicated process. So full modeling of the full molecular scale processes is exciting and promising and interesting, but it is not high throughput. You're going to study just a handful of materials at most over a number of years if you really want to understand it that way. So we wanted to take an approach that we could do much more quickly than that sort of full detailed atomistic understanding of all of the catalytic steps in executing the oxygen reaction. So we took what's called the descriptor approach. This is a kind of more data-centric approach. It has a long history that's been very effective, and the idea is very simple. You take some property, and here I'm showing an example of it. Don't worry about the details for the moment, but you take some property on the y-axis that you can measure experimentally. And then you take something you can calculate on the x-axis pretty quickly. And then you hope that they are correlated. And if they're correlated, you suddenly have a very powerful tool. So here, for example, is a classic descriptor approach that was pioneered by Jens Norskov now about 20 years ago, where he and collaborators looked at the activity of catalyzing the oxygen reduction reaction. So that's combining hydrogen with oxygen to make water, another important fuel cell reaction. And they looked at a measure of the activity that might be the current at a certain overpotential, something like that. And they simply plotted it as a function of something they could calculate easily, which was the binding energy of oxygen to the surface of the metal. And what they found, is they got this very nice volcano plot, it's called, where they could get a quite good correlation between the simple quantity and this complicated catalytic reaction. And the power of this is you don't need to fully understand all the steps in the reaction or be able to model them. You just need to be able to calculate the quantity on the x-axis and use its correlation to the property you care about on the y-axis. And they were able to use this, for example, to try and find the peak of this volcano where you would get the most catalytic activity of different materials. So it gives you ability to make predictions. It often gives you understanding of key physics, and it just makes a very powerful materials design tool because it lets you quickly get at a very complex physical property, even if you don't necessarily understand everything about that property and what's going on at the molecular scale. So we wanted to do the same thing, but for our fuel cell materials. Now, we were working with oxygen, not with a metal. And we actually tried the P-band as a descriptor and didn't really have much luck. Sorry, the D-band as a descriptor, which is a common descriptor people use and Norskov has used many times. But so you may have heard of that descriptor, but we found it didn't work as well. And what we realized is because we're working with oxygen, we needed a feature of the oxygen that might work well as a descriptor. So what we settled on, and I'll show you that this works reasonably well, is what's called the oxygen P-band descriptor. And it is just the distance of the P-bands, the center of the oxygen P-bands, to the Fermi level. So if you calculate a density of states, here's a very schematic density of states. There's a region of the quantum states of the electrons that are associated with oxygen that we call the P-bands. And if we take the center of that, it typically has a certain distance from the Fermi level, which is the highest occupied level of the electronic structure. And we took this as the descriptor. That's easy to calculate, comes right out of a typical quantum mechanical calculation. We use a technique called density functional theory to do our quantum mechanical calculations. And you can get the P-band center out of a calculation that, again, takes a few hours to a day, something like that. And we're going to show that this property has some good correlations. I want to take a little aside about correlations, though. Correlations can be very misleading. Just because you see a correlation of some descriptor with some property doesn't mean it's real. There's a great website called Spurious Correlation, which I encourage you to check out, where somebody has taken the time to find data sets that have correlations that are almost certainly not meaningful. So here's a concrete example of that, where it turns out the divorce rates in Maine and the per capita consumption of margarine in Maine are extremely well correlated. And the point of this is not to suggest that eating margarine causes you to get divorced. It's to suggest that just because even a pretty good number of data points look really nicely correlated does not mean that one thing causes the other. It could just be spurious. It can just be a coincidence. So if you're going to develop a descriptor, you really should make sure it makes some physical sense. You should make sure it correlates with a number of different properties. And it should really work on new data that you didn't fit it to when you thought it up. It should have some kind of predictive ability for new systems. So I want to show you that this P-band descriptor actually does this for a lot of sort of active oxygen oxide properties. So the first thing is, does it make any sense that it's going to relate to oxygen moving in and out of a material? And I would argue that yes, because when oxygen moves in and out of a material, it generally causes redox in the material. It either pulls electrons to the oxygen or drops electrons back in the material. So here's an example where you create a vacancy in an oxide. If you create a vacancy in an oxide, the oxygen usually has 2 electrons sitting on it. And when you pull the oxygen out of the material, those 2 extra electrons that the oxygen is pulled from cations in the oxide get dumped back into the oxide. If you think qualitatively what that involves, it means the oxygen P-bands that used to hold those 2 extra electrons drop them at the Fermi level. That's essentially what happens in terms of redox when you create a vacancy. So this descriptor, this distance between the P-bands and the Fermi level, should give you a really good qualitative feel for the energy of redox in your system. And that means it's going to capture things like the energetics to form vacancies, or to bind oxygen onto the surface, or other properties that involve exchanging oxygen and moving oxygen around in your system. And that is exactly what we find. So here are a couple of correlations with this oxygen P-band center. The idea really came out of some work from a student of mine named Yuelin Li, and he really thought of the idea. He should get credit for bringing it into the world. He was originally looking at surface exchange coefficients. That's a measure of how easily you can exchange oxygen with the surface of an oxide. And he looked across a bunch of perovskites. And he found that if you took the log of the surface exchange coefficient and you just plotted it as a function of the oxygen p-band center relative to the Fermi level, that descriptor I just described, then in fact, they fell pretty well on a line. And that meant we had a property that was very strongly correlated with the kinetics of oxygen in the material. Really, its ability to be an active oxygen material is really well captured by the surface exchange coefficient. And it correlated linearly with this very simple property we could calculate. So that showed a good strong correlation. And actually, he first realized that in 2011, and he had 9 data points. Since then, we've collected another 16 or so data points and added them to the plot, and they still fall on a line. So that shows that we didn't just make it up by cherry picking our favorite 9 data points. Over the years, every time we add a new data point, it generally falls on this type of correlation. We've also found that a lot of other things seem to correlate with this p-band descriptor. For example, we calculated about 40 migration barriers for oxygen to diffuse in a bunch of different perovskite systems, and we plotted them against this oxygen p-band center energy, and in fact, again, found very good correlation. As you increase the p-band, the barriers to move oxygen decreased in the system. It's not perfect. It's not like it perfectly controls the barrier to move oxygen, but there's clearly a very strong trend there. And we've seen this in other properties. So here are measures of actual area-specific resistance in a series of different perovskite materials. We plotted this as 2 lines because we think there might be 2 curves here, and I'll skip the details, but the qualitative result is that as you increase p-band center, area-specific resistance seems to decrease. So these are materials that were actually tested in a configuration for use as a fuel cell and showed that their essentially fuel cell performance, their area-specific resistance, trended in a pretty strong way with oxygen p-band. And even other properties that really have nothing to do with oxygen transport, but we've just been intrigued to realize correlate with this p-band center. Work function of perovskite oxides correlates with p-band center. This is calculations of a bunch of different work functions of a number of different oxides. And we found a pretty good linear correlation with work function, with p-band center. And it's important also that a result is usable by some other group besides your own. Those are all examples that we found. This is a study from Jens Norskov's group showing correlation of binding energetics of oxygen and OH, their relative binding on a range of different sites in a bunch of different oxides, again correlating with essentially the p-band center descriptor. So we really feel like there really is strong correlation across a number of properties across multiple groups. When people look at it, they continue to see these types of correlations emerge. So armed with that descriptor, we can now get access to really critical kinetic properties of these fuel cell materials without having to understand everything that's going on, just using correlation. And so we can use that to actually search for new materials. So let me show you how we can do that. So we're going to now screen for some promising perovskites. So the most important thing we want about them, well, here are 3 most important properties. And there are others which we didn't screen for, but these are the kind of top 3. You want them active with respect to oxygen. I want oxygen to move in and out of them really quickly, so they'll be great fuel cell electrodes. So I want a high surface exchange coefficient. I want them to be thermodynamically stable because I'm going to put them in a fuel cell at like 600 or 700 Celsius for 10 years. If they're not thermodynamically stable, they're almost certainly going to transform into something else. And if they're going to be an electrode, they have to be electrically conductive. If they don't meet all 3 of these criteria, there really isn't any interest in exploring them at all. However, if they're good in all these criteria, then they might be an exciting material to look at, teach us new things, potentially even impact commercial devices. So how do we explore whether they have a high surface exchange coefficient? Well, we have this wonderful correlation between the p-band center, which is easy to calculate, and the log of the surface exchange coefficient. So we're just going to use this correlation, and then we're going to calculate a lot of p-band centers. How are we going to decide if they're thermodynamically stable? Well, we're going to use a set of tools developed by the Materials Project, which is a very large database of hundreds of thousands of computed energies. against which we can compare any new perovskite and decide if it's stable. So they have a large database of energies and some very nice tools that let you basically calculate the phase diagram of any new material in light of all of those hundreds of thousands of calculated energies. So I can take any of our calculated perovskites and in just a few minutes decide, is it thermodynamically stable with respect to essentially all the known oxides and in the world, or metals for that matter. It's not, again, a perfect calculation. It's all done at 0 Kelvin. It has some approximations, but it's a very good qualitative guide, even semi-quantitative guide for thermodynamic stability. Then, how do I decide if it's an electrical conductor? There are a few tricks for this, but the major approximation is I make sure it doesn't have a big band gap. I can calculate the band gap when I do an electronic structure calculation. It comes out for free. And if it's large or even reasonably, half an EV even, it's probably not going to be a good metal even at high temperature. And then we would discard it from our list of candidate materials. So let me show you what happens when we do this kind of screening. You can basically think of it as a big inverse funnel. We set up a big list of automated quantum mechanical calculations. We explored about 2,000 perovskites guided by compositions we thought would be particularly promising. And then we basically looked at the surface exchange coefficient and we said it better be better than lanthanum, strontium, cobalt, iron oxide, because that's a commercialized material. If our performance is worse than that, no one's going to be interested. And then it better be stable. So we took a cutoff in stability that was 40 MeV per formula unit. That's basically the error bars of the DFT. So we said it should be stable within error bars of DFT. And we said no insulators, because no one's going to want to make an electrode out of an insulator. And then we basically used those to weed out everything that wasn't promising. And what we're left with are our most promising materials. So here's the list of all the calculations. Here's our surface exchange coefficients on the left axis, our stability on the bottom axis, on the x-axis. And we got our couple of thousand calculations, and the stuff we're really interested in is this region up here in the top left corner. This is highly stable because it's very close to the convex hull. Even on the convex hull, that gives us a 0 value of instability. Convex hull basically measures how close you are to stable. If you're on the convex hull, you're stable. If you're near the convex hull, you are likely very close to stable. And then high surface exchange coefficient is high up here on this axis. So we basically got rid of everything that was too low in surface exchange coefficient. We get rid of everything that is too unstable. I can blow up this region. Then we got rid of everything that was insulating, and we get these remaining circles. So our 2,000 compounds became 20 compounds. Then we basically ranked those. I put them here on our K-star plot. All these green dots are our predictive surface exchange coefficients for a bunch of materials that we had never yet made. We just had computed predictions that they would be stable, good conductors, and have reasonably good surface exchange coefficient. Then we picked a few to actually look at. Now you might say, shouldn't you just pick the best one? Well, there's always some trade-off of how easy is it going to be to synthesize? How hard is it going to be to get the elements involved? How many components does it have? The first thing we synthesize, we don't want to make it 7 components. That might be really challenging. So we picked what we thought of as a good sort of compromise of ease of ability to make it. Our intuitions told us it might be good. And we looked at a material called barium iron cobalt zirconate. There had been some previous studies of members of this family, but what was really interesting is our calculations told us that we should be able to make a material that was highly active and had a lot of zirconium. Now, if you don't have a lot of intuitions about these materials, this isn't probably surprising to you, but in the limit of having a whole lot of zirconium, this is 75% zirconium on the B site. In the limit of 100% zirconium, this material would basically be barium zirconate, which is an insulator. It's actually used as an electrolyte. So it shouldn't work really. And most people would say 75% zirconium is just too much. But we predicted that it would help with stability and it would still allow enough electrical conductivity that you could have a promising material and it would keep good surface exchange, which was really counterintuitive to most of the people we talked to. In fact, it was counterintuitive enough that they insisted on making a lower zirconium content as well, because they didn't really believe this was going to work. But once we made it, this is the actual measured surface exchange coefficients that we obtained from an experimental effort This is a collaboration with the National Energy Technology Laboratory. We were very happy to find that the surface exchange coefficients that were measured fell essentially right on the line that we had actually predicted. So these have some of the highest surface exchange coefficients of any materials that people have ever discovered, and at least at the 75% composition, have really quite good stability. So we're excited about these as potential future solid oxide fuel cell electrode materials. In fact, if you measure their diffusion coefficients, they also are excellent diffusers. Their migration barrier for oxygen diffusion is only about half an electron volt. That's one of the, in the range of the lowest that have ever been measured in perovskite materials, in fact, in any materials. And you'll see that if you put them on our curve of predictions with this oxygen p-band, we predict they would be right around somewhere in this mess of stuff at around 0.4, 0.5, 0.3, and it comes out at about 0.5. So it came out pretty close to our predictions, certainly well within the uncertainties of our predictive method. So we were very excited about this, both because it's an interesting class of materials and because it really validated that this correlative descriptor approach was yielding qualitative and even semi-quantitative guidance for new materials. Okay, so let me just finish up. Let me see how long I have here. I've got a few more minutes. So somebody stop me if I'm supposed to stop way early, but I'll leave 5 or so minutes for questions, if that's okay. Somebody can say
yes. Yeah, that'll be good.
All right, sounds good. So let me finish with a few thoughts on machine learning and this type of work. So there's been a lot of work recently in material science using data science tools, particularly machine learning. I've been engaged in a lot of it because it's really exciting. And there's a nice opportunity for it here in this kind of screening. So let me share how it might work. So if you think about what we just did is we said, let's take density functional theory, quantum mechanical data, particularly p-band, stability, band gaps. Then we add to it this empirical correlation of surface exchange with p-band, and we used it to find new materials. And that's great. It allows us to explore things really thousands of times, at least hundreds of times faster than you could do experimentally. But it's still true that a single DFT calculation takes on the scale of 100,000 seconds, right? Kind of 10, 20, 30 hours, something like that. Think of it as one day to get a good quality calculation out of these. And if you want a really good quality calculation, it might be 2 or 3 days. So that's still a pain, right? We still have a pile of computers in our basement that cost tens of thousands of dollars running 24 hours a day, every day for a year to build the database we need to do these kinds of screening calculations. So it takes a significant amount of effort. And it limits us to 2,000 or so compounds. But what if we could find a way to speed up that first step? Because that's really the rate limiting step in this whole process. So here's where machine learning can come in. Maybe instead of calculating these properties every time with density functional theory, one could find some very simple features, things that I know immediately, like composition, where the atoms are inside a perovskite structure, chemical order. Those are things I can just write down on a piece of paper or generate on a computer in fractions of a second. If I could machine learn the correlation, so find the connection between the DFT data and those simple features, find that correlation, then maybe I can actually screen from the simple features themselves. So that's what we did. We basically machine learned a relationship between these elemental properties, like A and B site composition properties, and these DFT data, and we replace this DFT data with machine learned data. I haven't done all of this yet, but that's the idea. And suddenly this goes from taking 10 to the 5th seconds to taking only a fraction of a second. So I'll give you one concrete example of doing this with the p-band part of the data. This is our machine learning of p-bands. We took all 2,000 calculations we had done. We used a technique called gradient boosting, where we correlated the p-bands we had calculated with features of the elements we had used, things like their melting temperature, their bulk moduli, their densities, properties of the elements. And we were able to predict back a new p-band that we hadn't looked at before with a quite good accuracy. We had a typical error of about 150 milli-electron volts in the p-band. You can see it ranges over almost 6 electron volts. That's a pretty small fraction of the error. And this is actually what's called a parity plot. It shows our predicted p-band centers as a function of the true p-band centers using machine learning. Now, by true, I mean DFT calculated, and by predicted, I mean using machine learning. So the fact that they fall almost on the identity line with a certain modest spread tells us that we can actually do a pretty good job of predicting p-band centers just from knowing the elements that are involved. And that this error, although it's significant, it's not nothing, corresponds to about half a log unit, or in K star. I should have said log K star here, about half a log unit in the surface exchange coefficient. Actually, that's about the error between any two experimental groups. So although we don't have a perfect prediction, experimental K star values aren't perfect either. So this actually isn't too big a deal. So now we can do something we couldn't do before. We can actually run through essentially every perovskite we can possibly think of and predict their p-bands, and then use that to predict their surface exchange coefficient. So we did that. We screened 2.1 million perovskites, which was kind of all the ones we thought were potentially interesting in terms of the types of elements they had. We looked at 19 A-site elements and about 20 B-site elements, built a grid of compositions, screened 2.1 million compounds, and found that we could get reasonable predictions on surface exchange coefficients as far as we can tell. Here are 3 or 4 known materials. We looked at their ranking. They go from about 730,000 to about rank 18,000 in the 2.1 million. And we predicted their surface exchange coefficients, and they fall typically within about half a log unit or a little bit more of the known experimental values. So now what we want to do is start looking at the higher ranked compounds. We still need to figure out a way to screen for band gap and to screen for stability that's equally quick. And then hopefully we can find even more new compounds that have really desirable properties. So this is ongoing work. We are not done with it yet. We haven't done it, but you can see how the machine learning might dramatically accelerate what you can do when you combine it with a lot of density functional theory training data. Okay, so let me wrap up there. Really, the message is that we can use this oxygen 2p band as a powerful descriptor for understanding and discovering new active oxygen materials, and integrating that with ab initio methods to kind of find the new materials, and then using the descriptor correlations to really connect it with actual experimental data. So I'll finish with that in terms of the technical talk. I was asked to give a couple of minutes of sort of career thoughts, I guess. It wasn't too specific, so I took my own spin on this. So here's my career thoughts. Take them with a grain of salt for what they're worth. Oh, let me just thank our group also, because they keep all the computers running and do the bulk of the work and everything. So I'm always very grateful to them, of course. So here's some career advice. And I have kind of eclectic career advice, so really take it with a grain of salt. But I think for all of you, I'm assuming most of the people I'm talking to here about this career advice are people in their kind of 20s, right? You're in graduate school, maybe a few postdocs, kind of that range of your career. So you have 50 years, easily ahead of you, right? Of science, I hope, and exciting research and things. It is hard to even begin to fathom what that might mean for technology. And here's why. You've probably all heard of Moore's law, right? Which says that semiconductor technology essentially improves by about a factor of 2 every 18 to 24 months. That is exponential growth, essentially, is what that describes. We all got very familiar with exponential growth during COVID, because it's the same way, unfortunately, that viruses spread. But it really depends on the doubling time, sort of what you're dealing with. So I thought this was a helpful plot. What I'm plotting here is on a non-log plot, the evolution of computer performance. This is the best computer in the world. This is the actual doubling time plotted since 1960. Doubles about every 1.1 year, the fastest computer in the world. So if you go up to 2022, which is about where we are, this curve at the bottom that doesn't do anything, this is what we have lived through. This is actually exponential growth since 1960. you look at it and you're like, that's not exponential growth, nothing's happening. But that's what's so weird about exponential growth. The next 10 years always looks astronomically larger than the previous 50. That's just, or 60, that's just how it works. So this plot would have looked the same no matter when you made it, but let's make it right now. Everything we have seen in computing, which has been absolutely world-changing, is approximately nothing compared to the next 10 years. That's what exponential growth means, assuming we're going to continue to see it, which all signs are that we are. So that's, of course, just computers, but computers drive a lot, right? And it turns out this kind of exponential growth is everywhere. You see it in genomics, you actually see it in battery efficiency and cost, you see it in solar cell cost. Many technologies are growing exponentially, not at the same rate that the computer is, so not as totally astonishingly, but actually some of them are, like genomic sequencing. So people have estimated this, and one way of saying it is the kind of growth we're going to see in the next 10 to 15 years will look like the last 100. And I will remind you, the last approximately 100 years is sort of everything. It's the car. If you stretch another 20 or 30 years, it's the phone, it's the computer, it's the television, it's the radio, it's all of modern society. The next 15 years may see all of that compressed into the next decade and a half. So that's kind of astonishing to think about. It means that for those of you who are starting your careers, now, I'm not even going to worry about me, I'm just going to retire. But for those of you who are starting your careers, the amount of change you will see while you're getting a job and getting tenure or getting established at your company or building your startup is just astonishing to think about. The other thing that's going to happen, right, is artificial intelligence is going to do a lot, and it keeps seeming to grow what it's going to do, right? And I don't think we need to be fear-mongering about that. It's not going to come and destroy our lives necessarily. Some, it might be, some jobs you have to think carefully about, but a lot of tasks are going to get taken over by artificial intelligence automation and associated robotics that bring that artificial intelligence into the world. And I refer to those as closed tasks. That's kind of anything you're going to repeat a lot, you're probably going to be able to train a computer to do it better. And that includes super complicated stuff like Go and chess. You can spend your life as a human mastering that, and a computer's still going to basically be way better at it. It almost doesn't matter how complicated it is. If it's repeated and you can let the computer see it 100 million times, they're going to get better than you at it. So that's the world I think most of you are entering in your job markets. And that means that adaptability is like the word of the day, because the world is going to change insanely fast. And you want to have a kind of mindset of somebody who's going to constantly be growing and evolving, because it doesn't matter how good you are at anything, it's going to be very different in 10 or 15 years. And you got to be ready to focus on things and learn hard new things and stick with them and get good at them and then move on to the next thing. And I think that was always a good set of characteristics, but it is ever and ever more true that it is what is going to make people successful. So what do you focus on as a PhD student, as a postdoc? I think these four things. Learn to learn. Now, everybody's always said you should learn how to learn. Okay, so it's always been true, but it's really, really true now. And I would think smart about this. I've noticed that I teach people to learn by handing them a textbook. That's probably wrong. And it's unfortunately because I'm over 50 and that's how I learned, and I can't get out of that mindset. But you as students probably need to learn from YouTube and Google and Wikipedia and who knows what else next. You probably need to learn from AIs that teach you how to learn in the near future. You need to be able to be flexible and learn how to learn efficiently and effectively on the timescales that are going to be necessary to be really productive in the rapidly changing world you enter. And you have to learn to tackle and solve unstructured open problems effectively. Learn to solve them and learn to tell a good story about them, because that's part of what it means to solve them, really, to solve them for other people. And that means telling a story to people about them. Now, that thing that sounds sort of vague, that's what research actually is, I think. So we think of research as some hard technical problem, but it's really solving and telling stories about hard, unstructured, open problems. And it could be technical, like how do I build a better solid state battery? But it can be, how do I make a better chat app for my community? It can be all kinds of complex, open, unstructured activities. You may be doing ones in your research that are really your technical research, but they may be any other kind of business problem, or even designing the perfect class for students in a high school is a hard, open, unstructured problem. And then I finish off with take some time to figure out what you're really interested in and passionate about and good at. Because as you have to move quickly and evolve things, knowing kind of who you are and what you really like will help you make good choices quickly as everything gets thrown at you. And then go ahead and learn technical stuff about your discipline. That's usually what you think of when you're getting a PhD. I better learn all this hard technical stuff, learn all these equations, learn how to code this stuff, learn how to do these difficult TEM experiments, whatever it is. I'm not saying that doesn't matter. I would just put it forth because I think it's a part of your life, but all these other things actually may dominate your life. Even if you go on and become a faculty, and I am a faculty, and these other things still dominate my life. So it's a little counterintuitive, but worth thinking about. And I finish with this quote that is not actually from Darwin. You can find it on the web. Apparently he never really said it, but it sounds good anyway, right? Which is that it's not always being the smartest, it's not being the strongest, it's not being the best, it's being adaptable and ready to keep adapting and moving in response to what you see that may become the sort of dominant thing that makes you successful in the world. So keep that in mind as you move forward. That's my advice. Take it for what it's worth. But with that, I'll wrap up and happy to take any questions.